Hi everyone, this is Junxi Ma from Institute of Software, Chinese Academy of Sciences. I'm very glad to demonstrate our work involving ultra-wideband in consumer-level devices into the ecosystem of wireless sensing. Let's begin with the background and motivation. In the past decade, we have witnessed the rapid development of wireless sensing technologies, including Wi-Fi SSI, RFID, and LoRa. These signals, originally designed for communication, are now supporting sensing applications such as human tracking, gesture recognition, and vital sign monitoring. Although promising, we found that all technologies mentioned above are unavailable on any consumer-level devices. For Wi-Fi SSI, it is only available on few dedicated devices. For RFID, it requires expensive RFID readers. And for LoRa, it is rarely seen in daily use. On the other hand, we observe that an increasing number of consumer-level electronics are now supporting UWB technology. In 2019, Apple took the lead in releasing the iPhone 11 series integrated with U1 UWB chip, which offers accurate ranging between phones. Following this trend, Samsung, Xiaomi, and Google started to equip their products with UWB, including smartphones, smart tags, smart speakers, and even more household appliances. So here comes the question. Can we use UWB on these consumer-level devices for wireless sensing? To answer this question, let's first take a quick view on the principle of UWB. Different from traditional narrowband signals, UWB has extremely large bandwidth of more than 500 MHz, which is 10 times of Wi-Fi and 100 times of RFID. By utilizing the large bandwidth, accurate ranging and angle estimation can be both achieved on consumer-level devices. The ranging error is less than 10 cm, and the estimation error of azimuth and elevation angle is less than 3 degrees. With distance and angle information, we can localize the device in 3D space. Given a smartphone and a smartwatch, the azimuth angle, elevation angle, and distance of the watch relative to the phone can determine its location in a coordinate system. If the smartphone moves, we can also track its moving trajectory with a single device. Since we can realize accurate localization between consumer-level devices, we then ask the question, what sensing application is the most appropriate? Our intuition is that when a person wears a smartwatch or carries a smartphone with UWB, his movement of the hand and body can be captured by other UWB devices deployed in home through UWB connection. So, in this work, we designed two typical applications on consumer-level devices: handwriting recognition and multi-target tracking. Next, I briefly introduce our system design. First, we designed an app to enable UWB connection between consumer-level devices. It has the following features. It supports one-to-many connection between devices using time multiplexing. It supports reporting the distance, azimuth angle, and elevation angle of the pair device. It currently supports phone-to-phone and phone-to-watch connection and will support connection between more devices in the future. We then introduce our sensing framework for consumer-level devices. It has three parts. The first part is data collection. It obtains UWB data from our developed app. In handwriting recognition, continuous recognition for word-level handwriting is supported. In multi-target tracking, we can track multiple persons' trajectory simultaneously. Next, I will use two videos to demonstrate our system. The first demo is handwriting recognition. The user with a smartwatch will use the smartphone on the table to track the motion of the user's hand. The tracking result is shown on the TV in real time. We evaluate the system by recruiting 10 volunteers to collect word-level handwriting data. This is part of the handwriting result, and the recognition accuracy is all above 85% across 10 volunteers. The second demo is multi-target tracking using a single device. We use an iPhone 12 as the anchor to track the targets. 2 of them carry a smartphone in their pockets, and the other with a smartwatch. We can see the tracking result on the map. We use an optical-based ground truth device to evaluate the tracking accuracy. We asked the volunteers to walk in different trajectories and use a single device to track them. For one person, the tracking accuracy is 7.5 centimeters, and for 2 persons, the accuracy is 8.6 centimeters. That's all for our demo. Thanks for your time.